Welcome to the Explainer. Today, we're literally opening up the Chemist's Toolkit to demystify how scientific discovery actually works behind the scenes. We'll be zeroing in on the fundamental tools of chemistry, the things that turn abstract, high-level ideas into the tangible products we rely on every single day. Here is our roadmap. We'll start with the physical lab tools, then get right into measuring and handling samples. After that, we're going to transition to the mental tools, the scientific method, the crucial difference between accuracy and precision, and the math and conversion factors that glue it all together. Finally, we'll wrap up with real-world consumer chemistry. All right, let's dive into Section 1, the physical lab tools. Now, you might have noticed that chemists don't just use ordinary glass. Whether we're talking about a round-bottom flask or just a basic test tube, they rely heavily on borosilicate glass. You probably know it by brand names like Pyrex or Chemist. The reason? It's all about stability. Borosilicate glass won't just suddenly shatter when it's exposed to hot solutions or rapid temperature changes. It's a real game changer for safely carrying out reactions. And honestly, the simplest hand tools in our kit are just as crucial. Take a look here. On one hand, you have the spatula, which is basically a specialized spoon for scooping and weighing solid chemicals safely. On the other hand, there's the trusty stirring rod, sometimes called a glass baggot. It's solid glass and absolutely essential for mixing liquids without cross-contaminating your whole reaction. They seem super basic, right? But they're literally the extensions of a chemist's hands. Of course, to make these chemicals actually interact, we usually need to add some energy. That brings us to fundamental equipment like the hot plate you see here. Instead of relying on open flames from a Bunsen burner, which, let's be real, can be pretty dangerous around flammable solvents, modern hot plates give us controlled, steady heating to drive those reactions forward safely. Moving right along to Section 2, measuring and handling samples. So, having containers and a heat source is a great start, but to actually do chemistry, we need to know exactly how much of a sample we're working with. And I mean exactly. This beauty right here is an analytical balance. It is definitely not your average bathroom scale. It's an incredibly sensitive instrument designed to give us the exact mass of our materials, often down to a fraction of a milligram. See those little glass doors? They're literally just there to stop tiny air currents in the room from throwing off the measurement. That's the level of exactness we're talking about here. But, not all samples are just simple powders you can casually scoop on a scale. If you're analyzing something complex, like blood, you need highly specific tools. Drawing blood means using syringes and stainless steel needles, and then transferring that sample into evacuated glass vials with rubber caps. Those are called vacuitainers. Oh, and if you're analyzing blood plasma, you actually have to add an anticoagulating agent straight into the tube to stop it from clotting. So the toolkit really has to adapt to whatever matter is being studied. Okay, so at this point, we've collected our samples, heated them up, weighed them out. But here's the million-dollar question. What do these measurements actually mean? A fancy beaker and a hypersensitive balance are basically useless without a mental framework to interpret all that data. Which brings us to Section 3, the scientific method. This is where we shift from the physical hardware of chemistry to the software, right? The operational mind of the chemist. The scientific method is our ultimate conceptual tool. Historically, early alchemists did a ton of tinkering, but modern chemistry formalized this whole process to make sure discoveries are based on reproducible data, not just guesswork. It's a continuous loop. You formulate a question, you make a hypothesis, you run experiments with your lab tools, and then you analyze the results to form a solid conclusion. Think of it like this medical analogy. When a patient walks into a clinic, the doctor doesn't just pull a diagnosis out of thin air. No way. They check the symptoms, ask questions, and lean on their medical training. In the exact same way, a chemist reads the scientific literature and uses prior observations to formulate a highly educated guess. And here is a huge misconception we see all the time in everyday language, mixing up hypotheses and theories. So let's clear this up. A hypothesis is your initial, tentative attempt to explain a specific problem. It's that educated guess. A theory is a deeply reliable, well-established framework backed up by an overwhelming mountain of experimental evidence. If a new fact contradicts a theory, we don't just throw the whole thing out. The theory gets modified, which actually makes it even more robust over time. And when a pattern emerges over and over again, completely without fail, we elevate it to a law of nature. For instance, the observation that heat naturally flows from a hot object to a colder one, that's a law. It simply summarizes what happens, with absolutely no known exceptions at the time it was formulated. All right, let's get into Section 4, accuracy versus precision. Think about a dartboard for a second. We tend to toss the words accuracy and precision around interchangeably in daily life, but to a chemist, they are totally different concepts. Accuracy is about actually hitting that bullseye, how close your measured value is to the accepted true value. Precision, on the other hand, is about hitting the exact same spot repeatedly, whether it's the bullseye or not. It's all about the repeatability of your result. So the crucial takeaway here is this: good precision absolutely does not guarantee accuracy. A chemist can be incredibly precise, landing on the exact same data point 5 times in a row. But if their physical lab tools are busted, say a pipette that's poorly calibrated, they've got a systematic error, so their highly repeatable data is just uniformly completely wrong. Moving to Section 5, math and conversion factors. Let's look at the mathematical tools that let us translate all that precise, accurate data into something we can actually use. Math is the true language of chemistry, and conversion factors are our everyday translators. Just like you intuitively know that 1 hour equals 60 minutes, a conversion factor lets us seamlessly jump between different units of measurement, like going from grams to moles or milliliters to liters. And the best part? It doesn't alter the real-world physical amount of whatever we're studying. Here's how we actually use conversion factors in real chemical reactions. Just look at the balanced equation for water. 2 parts hydrogen plus 1 part oxygen gives you 2 parts water. Those numbers in the front, the coefficients, are actually built-in conversion factors. By setting up a ratio with them, a chemist can predict exactly how many moles of a product will be created if a certain amount of reactant is consumed. It's basically a perfect, predictable recipe. And finally, Section 6, real-world consumer chemistry. So, we have to ask the big question: why does mastering all this hardware and software actually matter outside the lab? Well, when you combine physical tools like analytical balances with the conceptual frameworks of the scientific method and precise conversion factors, you get the massive world of consumer chemistry. Almost every single household item you own, from those brightly colored detergents under the sink to the meticulously formulated cosmetics in your bathroom, is the direct, practical result of applied chemistry. Chemists are constantly manipulating matter to make our lives better. By understanding reactions like saponification, they can turn ordinary oils and fats into powerful soaps and cleaners. They use emulsifiers to keep our food the perfect texture, and the field is still evolving fast. By integrating nanotechnology, we're making products incredibly efficient right down to the molecular level. Meanwhile, the boom in green technology means industrial processes like wastewater management are getting way more environmentally friendly. So we've explored the fundamental tools of chemistry today, taking a journey from basic borosilicate glass and hot plates all the way to the abstract theories and math that drive scientific discovery. Which leaves us with a pretty fascinating thought to end on. As these laboratory tools become even more advanced, what incredible, world-changing solutions will they build next? Keep an eye on your household shelves, because the chemistry of tomorrow is already being formulated today. Thanks so much for joining me for this explainer, and keep questioning the world around you.